Welcome all. Thanks for being here. Today you're going to learn from one of the real experts at FruitPunch. We know a lot about AI, but there are many domains we don't know a lot into the specifics, and that's why we invite real domain experts. I actually work with this type of data a lot. I'm very familiar with the specific domain, and that can give some of their tips and tricks and prevent some of the pitfalls that you might fall into when you work with this type of data. For that today, we invited Federico from Space4Good, but I'll let it up to him to introduce himself and Space4Good, where he's from.
Great, thank you, Sako, for inviting me, and I will start to share my screen. Welcome, everyone. As I mentioned by Sako, I will introduce you a bit to the world of GIS and remote sensing. Please confirm if you can see correctly my screen.
Yes, you can.
We can.
Great. Thank you so much. Short introduction of myself. I'm Federico Franciamore, originally from Italy. I have a background in environmental science, but then I moved to the Netherlands after a short period of working with the Italian startup, remote sensing and Earth observation in general. And another experience in an oil and gas company. I moved to the Netherlands to start my master in Geo-Information science. So I study at Wageningen University, and I joined Space4Good now for basically 1.5 years ago. And I'm working within the team, really international team, on different type of projects as a GIS and remote sensing specialist and designer, because I have a passion for the design as well. So as you will see soon, describing shortly what we do, we often find ourselves to design some platforms or digital environments. So I take care of the UX and UI parts. Well, Space4Good, it's in our name, Space4Good, and Earth observation for social and environmental impact. What is the agenda of today? I will just introduce you briefly to the company and a short moment on the type of project that we run, so you can have an actual example of the type of applications that we conduct and we develop together with our partners. GIS introduction. So we'll go really to the basic of the knowledge of the GIS, what is GIS and what are the type of data that we can use. And an exercise, I guess you had already the link to work with in Collab. If someone has some issues on that, you can write in the chat, I guess. And then after a moment of the exercise, we will go through a remote sensing introduction as well. So what is remote sensing in general, and an exercise accordingly. Last moment is for Q&A. So if you have some doubts or how to retrieve data, I guess that would be useful for your experience. Space4Good was founded in 2017, the European Space Agency, BIC, the Business Incubation Center, and we are at the moment 10 full-time employees with the other 8 interns and quite a few freelancers as well that join us usually when some projects specifically kick off. We are located in The Hague. I'm actually right now here at the Humanity Hub. It's a co-working space with other NGOs, and we are basically a social enterprise. So this means that part of our income we reinvest in other projects. We open innovation and co-creation. We develop our projects, and we have quite a few type of clients and stakeholders which are located usually around the globe. This allowed us to stay in the forefront of meaningful, obviously, innovation and open innovation, and we co-create the solution together with them. We are based on three main pillars: remote sensing, as I mentioned before, Geo-Information science, and AI. These are the three pillars that we base on our daily work, basically. And what we offer monitoring and detection, assessment, and mapping and modeling and prediction. How we do so? With a small part, specifically for the small projects of research and advisory, we run these quick scans to first check the availability and the feasibility of the project, because obviously is always a research with this in this field, and what are the suitable data to use for specific projects. We co-develop and integrate the solutions that we find, and then we develop the applications or APIs through which the client can actually access this type of data or information. As I mentioned before, we found ourselves as well to actually develop from scratch web platforms. More part of our work is dedicated to traineeship and workshopping. So yeah, this moment is actually one of those. We are active in many sectors, from agroforestry, precision agriculture, and forestry. I have to say a big part of our work is dedicated to this second sector: peace and justice, climate change, the infrastructure monitoring, and as well as ecosystem services and biodiversity conservation for conservation purposes. Then I will go really quickly to our project portfolio just to give you an idea and an introduction of what the type of project that we actually are active in. So, for example, for forestry, we have a project with the canton in Switzerland about bark beetles infestation. So this helps the management of the forestry with satellite imagery. We are able to detect pests and disease. And so we develop a risk model. So we launch the alert, and this is merged then with the in situ data, and help, as I said before, in the monitoring and the management of the forest. We are quite active in the fire detection sector because, yeah, as you can imagine, is a big environmental issue, especially lately. Just came back from Sicily, where this summer was a mess with the fires and wildfires. How we run, so we created specific platforms where we have these fires alerts, fire risk maps using different type of parameters, and we launch the alerts when we think might be the case of a fire, but we use as well active fire products as the one delivered by the NASA. So we have this kind of integration with this type of data. We run this with our study group, which is a company based in Indonesia. Something that we did in the Netherlands, I have to say, often we find ourselves working abroad, but a couple of projects we've been involved with were as well in the Netherlands for the NFI, so the Netherlands Forensic Institute, to detect clandestine graves using different type of data, so optical, radar, and LiDAR as well. And we used in this case, because the resolution often is not super optimal, exclusion instead of detection. So instead of detection, the graves actually went on the all way around. Big project that I was involved personally was this emission monitoring for the NOx and specifically NO2 monitoring platform that we conducted with the World Bank Group. And we used for this such a purpose, we use Sentinel-5P. It's a new, relatively new type of satellite data launched always by the ESA, the European Space Agency Copernicus program. And yeah, the goal was to see if such type of data, satellite data, national level, could be, first of all, scaled down to regional agencies levels, and if these data are somehow correlated to the social economics development indicator, so basically the GDP. And we work together with the economists at the World Bank to see if this type of data can be used as a proxy of the GDP. And we did run this project for Vietnam, Indonesia, as you see in the map, and some MENA city in the eastern country. Another type of application that we find ourselves to work with is storytelling. So story mapping has a specific type of name where you kind of want to tell a story with a map. And we did this project with Fairphone for fair trade mapping. In the field of peace and justice, instead, using radar satellite imagery to detect changes in the surface in war zones, to analyze together with the Carter Center and the Allo Trust if there were some places where some bombs didn't explode yet. So trying to merge our observation and their data set to see if this was something detectable, and actually had quite few really good results. And then probably more closer to your domain of the AI, we had this project with the Gemeente of Rotterdam and a firm of architects for rooftop analysis. So classification of rooftops using deep learning based models and open source data, which luckily we have quite a lot here in the Netherlands because we have high resolution imagery every year. Unluckily, this is not possible to have it for the rest of the world, specifically in our area of domain. We work often in tropical areas. And this project was basically for establish what was the optimal potential of the use of this urban spaces, and specifically the rooftops. I want to talk to you a bit more deep about this project. Instead, is Reforester is one of the biggest projects that we are running right now, and it's the creation of an integrating agroforestry monitoring, conservation, and management platform. We're doing this in collaboration with our study group. And it's basically, the problem that was existing in this area, conservation in Borneo Island, Indonesia, was that all the knowledge was relying just on few local experts. And the traditional methods that we've been using are not good to cope the always more urgent problem of the climate change. What was the challenge? To develop an application that could have and use new tools, approaches, new type of data. And we came up with the solution of developing this web platform, which integrates a lot of applications together and provides better decision-making, rapid actions. These are the type of satellite data we use for this application. As you already see, in red, the commercial ones, in green, the free, the open source. Obviously, both of them comes with pros and cons, because the commercial ones have higher resolution, but they have more costs, as you can imagine. And then the free open ones, lower resolution, but the availability is for free. So this doesn't go in extra costs for actually purchasing data. The application that we were running here for this platform are many, as I mentioned before. So satellite archive, fire detection, change detection, biomass assessment. And instead of just listing them, I want to quickly show the platform itself. I will probably run a bit faster. So one can access this platform, and there is a fire alerts. So someone who is in the field, because we strictly work on people on the field, could check where is the area, what is the fire detected, then validate as well this detection. And then use really valuable information where, for example, to find the closest fire brigade to cope with this fire. These and many more are in our portfolio. I just invite you to visit our website and the portfolio over there. And that's it. Now we can start actually with the workshop. GIS introduction. First of all, well, what is GIS? So GIS is a Geo-Information system, and it's a scientific discipline that studies the techniques to capture, represent, process, and analyze all the geographic information. What we do with GIS? With GIS, we can integrate many types of data, and we can do this in a stack of layers, as shown here. So the one map that you will see just in a printed map would be such a thing. So a bit more confusing. With GIS, we can integrate all this layer together, and for visualization purpose, we can have it in a better and more organized way. Software and tooling. Someone say that if Facebook is the who and Google is the what, Esri is the where. So the signs of the location. Esri is a commercial company. It's an international supplier of geographic system tools and softwares. And on the other hand, we have QGIS, which is a free and open source platform. Behind there is a huge community of developers and users, and we have as well scripting. So we can work with different geospatial data by scripting. Today we work with the Colab, so in Python environments, and as well Jupyter or Google Earth engine. I will talk about this later on. Before going ahead, we can introduce a bit, probably most of you knows, but just could be a nice refresher. What are the coordinate reference systems? So CRS. CRS are coordinate based local, could be local, regional, or even global systems, and are basically thanks to them, we are able to locate geographical entities. The CRS have usually three components. So the datum, which is a model of the shape of the Earth. The projection, which is a mathematical transformation of a sphere when we pass from a sphere, so 3D to a projected 2D surface, and additional parameters that are often necessary if we want to move from one CRS to another one. In order to use, as I mentioned, data or from different sources, for example, we should always be aware of the CRS of our data. And this will be part of our exercise, because obviously this has to, overlay. This layer needs to be in the same coordinate system to have a proper analysis. And this transformation actually between the coordinate systems can be done using, as I mentioned, the transformation parameters, something that we will look at in the exercise. These are a bit recapping example of the datum. As I said before, is the model of shape of the Earth. Can be local or can be even global or Earth-centered datum. And basically, what are the difference? That a local datum just fits more, can fit more specific part of the ellipse. And the Earth-centered datum has a pretty good, well fit overall the Earth. In our case, in this example, we are in the Netherlands now. We have Amersfoort as a local one, but the most used ones, the Google Earth, for example, Google Map uses WGS84, the global one. We have to talk about data as well, luckily, and the main two type of data or data layers that we have, especially for geospatial analysis, and the ones that we will deal with today, are rasters and vectors. The main two difference between these two type of data are basically one is composed by pixels of pixels, while the vectors are composed by paths. And you can imagine a raster as a photo that you take with your cameras, like a JPEG, and so it's an array of various colors and pixels, which is the smallest units of the image that together form the image that you took. In our domain for the vectors, we have three main type ones: the lines, points, and polygons. With the rasters, and as well as layers, the vector ones, we can actually conduct some algebra. So we can do some calculations, some sum, for example, or even a least cost path. And with vector data, some of the example that we will see soon are the buffer. So basically create an area of buffer around a certain feature. So it could be a point or even a line or even a polygon or a clip. So it works having two features. It works kind of a cookie cutter. So with the clip feature, we can cut exactly the inputs. I will share this presentation with you, or even this main information slides that recap a bit the source of the data. So, well, where to find vector data. So usually for geospatial data, the first thing that one does is go into a geoportal, because each country has its own geoportal database. I have to say that some are more elaborate, organized, some other ones are not, but in general, this is how we start. And then there are some entities that collect all these data sets together at European level, but even globally. So you can find the links over here. Well, we can go ahead with the exercise. I hope you all are in this status. You received the link, and probably there was a link to Google Colab as well in the chat. And probably you made already a copy of it. So, well, I will run. Let me know if you all are able to actually download this folder from Google Drive, because I heard from Sako that sometimes could be some issues. In that case, I created different other folders. So you need just to change this ID. Try one of those if you have issues, and then change the name of the unzipped file, which in this case would be data1, data2, data3. Probably it's nice to wait a couple minutes or seconds to see if everyone is on track. I don't see any questions or doubts in the chat, so I guess I will keep going. So, well, once you unzip the data, oh, I should do both. Obviously, we need to install some packages. Maybe for who studied already or did some works with statistic plot libraries, something that usually use Geopandas or raster are specific for this type of tasks using geospatial data. There is someone probably in the chat. So use Python or QGIS. We will use Python actually. We can check it out, QGIS. I have to say the QGIS is something that as Space4Good we use just to visualize a bit better and to play a bit because it's a Geo-Information science system. But today, for the purpose of the exercise, we will use this Colab environments. Okay, so all the packages are installed, and before even probably there's going to be some of you still waiting for them, I can start to introduce you to the issue, the task that we have today. We'll have two exercises. The one relative to GIS is basically to find, the task is to find the suitable area for installing a new water pump between two cities in India, Theni and Kumbon, and what are the requirements? The city, the water pump has to be maximum 25 kilometers away from the city of Theni, 15 kilometers away from the city of Kumbon, and maximum 1 kilometers away from the closest water stream. So, well, these are the requirements, and we can import all our libraries, set the work directory, and we can start to read the location, for example, of the first CD. Well, we can set just, this is already in the exercise, so to find the file path for the specific shape file. Using the Geopandas library, we can actually read this file. So it's GPD. Here I imported the Geopandas library as GPD. And we can, first of all, read this file. So we can just type the name of the file path, of the file, of the data file. So we can and this is the information that we got. So for basically we have the name, longitude and latitude, and the geometry. This is an important factor because it's not just a CFC file, has even the data type is a point, and well, it's the only point contained in this data set, in this shape file. Shape file for it's a type of vector file, so for who is not really familiar with. So we've been talking quite a lot about the CRS, about the coordinate reference system. Let's check what is the coordinate system of this data set. So we can just write .crs. And well, we will have all the type of information we will need. We will have the datum we were talking before, and CRS over here. We will, from now on, at least taking this decision, we will choose to either convert everything to this CRS or make sure that the rest of the data sets are in this CRS, to make sure that the analysis can be conducted properly. We can read some districts in India. Just for clarity, I guess, what we have actually in this folder is some Indian districts, some water stream and Theni city in vector files. And then we have a CFC file containing some data. So we'll go through this data set contained in the Space4Good folder, and we will extrapolate and import it in here. So we were here. So we did read the districts in India. We can show the attributes. So again, let's check it out what it's inside. We can even print it this time. Otherwise, we can just type district. And we will go through all the different components of this data set. So we know now that are 91 actually, because yeah, we start from 0, 91 rows, so 91 elements and 6 columns. The columns are the properties instead. So we have some extra information of the name of the district, for example, and the data type. Could be a polygon or even a multi-polygon. It means multiple polygons attached together. Probably these regions have different areas of domain. Yeah, well, we can even check because most of the time we don't really need all the type of data. So if we decide that we want to look at just the first 5, let's go for it. And basically, it's just always matter to be able to, in a more organic way, see whatever you need to. Let's visualize the entire shape file. So these are actually the informations that we have in the table of attributes, but now we want to plot such data. How we do so? Again, districts df dot plot. So we want to plot them, and we have to add some obviously parameters. So the column that we want to visualize is the district. So this one here, because it's different, each one has its own. So we can type district. And then, well, we have to add here another specific parameters that is requested. So CMap, oh, sorry, I'm still CMap equal to known. So once you had this line, we'll be able to, and we run this line, we'll be able to plot this data set that in this format is in a table, but it's actually a geospatial data. So if we run this is actually a plot of the data set. These are some districts in India, are not all of entire India, but just in the south part. But well, between these, we need just a tiny one. So we want to work just in this tiny district because these 2 cities, Teni and Kumbun, are located in this district, and the analysis is just related to this. So what we can query and just slice one of these districts, acting here in the missing parts, the column district. And well, we need Teni now, so we can type here which district we want. In this case, is Teni. So the Teni district will be this slide, and again, we can visualize with the same methods just the Teni district. Let's do it like this. We can copy and paste this plot. It should be a bit faster. But this time has to be Teni district. Here we go. So yeah, now we plot actually just the district that we need. If you take care of this other map, it was this little district over here, and we will run our analysis on this specific location. We can print as well the CRS, and well, we noticed that these are different CRS. So as a reminder, we checked the previous one, and this was the 1,24344. The one that we have here is 4326. So in this case, we have to change it. So the output that we want in this code here is the one that I just mentioned, the decided one. The output reprojected directories are here. So the thing that we have to do is reproject this Teni district in the same CRS of our Teni city. How we do so? We can do it in here. So Teni district is equal to Teni district dot to CRS. So we want to change the CRS, and the one that we want to use for this change is the output CRS. So output EPSG. We can run. There is an error in the name. So oh yeah, sure. We didn't run this cell, so still needs to run, and now we'll have the reprojected. Well, this already happened, but to make sure, we will just check the coordinate system, and now you see that Teni district has the same one of the Teni city. So we passed from this to this. Okay. Now we have both data sets in the same projection that we want. We can save it because we want to be sure to be able to open this data set in our QGIS system or another GIS formats. And so what we do is any district, so we save it as like .to file, and well, we can use the output, so the directory that we want to save it in here, where we want to save this. And an important point now is the format that we want to save it to. So we can save it as the driver. Here we have to insert the type of format that we want. It's for sure vector files, but vector files means nothing because we can have different type of vector files. The one that we work usually is a S3 shape file. S3 shape file. This gives you a bit an indication on how S3 is well, one of the most used company or most used and known company, because they developed this actual format that became something to use for the rest of the community. So we save it now as a S3 shape file. This will be for sure in your folders. If you go for it, you will find it in this Geojson, in these vectors, for example, or Geojson folders. You just have to go check it out, and you will have this Teni district EPSG with the right format, the right CRS. Sorry. Well, this is just one type of vector files, but we can even save it as a different format. Another common format is Geojson. Probably you all know what is a Geojson. What are the pros of using such a type of data? With the S3 shape file, we'll have, if you go check your folders, you will have different type of data. So not just the shape file, but even these other ones. And we all need this in the same files to open, for example, a shape file on QGIS. If one of them is missing, basically the file is corrupted. With Geojson instead, so we always have taken care of having this 4 or 5 files in the same data folder. Or with the Geojson, is just one specific file, and it can be used to open it on QGIS as well. And then we can even convert if you really need a shape file. Well, if we write here Geojson supposed to save in Geojson formats, probably. What is wrong here? Oh yeah, the directory is, I guess, wrong. Oh, there is already something there, so we can change. I will just switch to this directory, I guess, because it was already saved there. Something with the same name. So we will actually have these two files saved. For the purpose of the exercise, we don't need to go and explore these files farther, but we know that are already stored in our folders. Well, keep going and look in our data sets. What we need are the water streams. Let's read them. Let's check it out. CRS, it's in the correct one, so we don't have to reproject any of this data. And another little exercise you will find if you work with this type of data to deal with CSV files. So usually they don't have an actual geospatial component, but we will try with this code now with these cells, the following cells, to actually pass from a CSV file to an actual geospatial data. As a context, can you actually see my other window here?
Yes.
Yep. So the CFC file that you will have in your folder is basically just a normal CFC file with just three simple properties, 4 simple properties. You will have the ID, the name of the city, longitude and latitude. So once we read this file, we can we have to make sure that this is read into a Geopandas or Pandas library. So we have to type here read CSV, and we will already there are settled here the parameters that you need for having this read. And if we run the cell, you will have here this CSV read by the system. What is missing? If you look at the previous data here, we had name, longitude, latitude, and then the type of geometry. And we don't have this yet, because for our environment now, for this stage, we have still, we are just reading the CFC, and we don't have any geographical information about this. We do this always with the Geopandas library. So we can use this to give the longitude and latitude this function, and then we need to add as well the coordinate system that we want. This is specifically what we have, because it's in the system as before, but we want to reproject this into our actually CRS, the one that we've been using so far. So we have to import the geo data frame into geo data frame and change the reprojection. So CRS into what? Into one that we want to actually have it, that already the rest has. Oh, just copy instead of paste. So if you remember the one that we have, and we need this one, so 24344. Okay, so this part of the code shortly basically create a geo data frame, because the CRS original one is the one wrong, so we reproject it to the one that we want. And as a final thing, we can print the data to see if the CRS is correct. Geodata frame. Okay, let's run this. I'm sure. We can print it. Well, as you can see, now we have our data in with the geometry and geospatial factor over here. We are ready now to plot this. I prepare already this part of the code, basically just plot all these three data sets that we've been working with: the Teni district, the Kumbun city, the Teni city, and the water streams. You just need to plot them. So you can just type here plot show. And then finally, with this, according to these colors, we will have a nice visualization and plot of the data that we've been working on. As you see, for sometimes we reproject this data sets, so they are all existing in the same area. Now we're working with the huge amount of data. So what we do usually is to use as less possible, trying to clip this data when not needed, so the machines work better. But a nice exercise is actually to clip two vectors. So what we're going to do now is basically clipping this watershed that are, as you see, outside the area of interest, outside the Teni district, and keep just the ones inside. So we can set in this new phase the actual directory and make the clip. How we did run the clip, always using the Geopanda library, Geopanda that clip. And then what we want to clip, we want to clip actually the water streams. So the water streams data file. The second vectors is the second vector is instead the region of Teni, so the Teni district. Teni district. We can run this line. We could visualize. We will visualize later on, but before visualizing, actually, we can save it as well in our folder. You can just run this line. It's the one that we've seen before. We're saving this line, this clipped file as our output water clipped in the format of S3 shape file. And now we're ready to visualize this, to plot this. So as you can see, everything now is contained into our area of interest. We have the watershed, we have the two cities. Everything looks good. We can start actually to do the analysis now, because now this was all the process to come to a cleaning and projection of the data to make sure that this is all settled. Just as a reminder, what were the requirements for the task? This water pump needs to be installed max 25 kilometers from one city and 15 to from the other one, and maximum 1 kilometer away from a water stream. So what we have to do, it's a buffer. We mentioned before, the buffer operation is basically creating this area around a feature. And there is already an example for Teni cities, which is 25 kilometers. We can do basically the same for the other two vectors. So we have to just change the name. So Kumbum GDF here. And the requirement was telling us 15 kilometers. So this time, just 15, and same for the water streams, but this time we have to just do a buffer of 1 kilometer. So it's, as you can imagine, it's in meters, so we need to add 3 extra zeros. We can run these buffers and we can plot them. So this is the result of the buffers around the different features. What we need now, this is visually, we can already kind of imagine that the area that's fulfill or the possible areas that fulfill the requirements are 2 and probably around these areas. But yeah, working with much more data usually is quite impossible to do this as a manual check. So what we can do is basically clip and make an intersection of these buffers. A first example is here, always with the Geopanda library. So we intersect the water stream clip with the Kumbum city to have the first intersection, and then the first intersection is intersected again. We can copy and paste this line. So as I mentioned before, right now, the first intersection, the result of the first intersections are clipped to the third data set, which was the city of Teni. We can run this show, and well, let's see what happened. You can see here in aquamarine color the 2 suitable areas to install a water pump. Something that we can do just running the cell is just plotting actually this area, this intersection results, and we can save them. What does it mean? Basically, now we found, probably it's nice as well if I open QGIS environment in the meantime as just a visualization. Basically, we find the 2 suitable areas that fulfill the 3 requirements and where the water pump can be installed. We saved these somewhere, so I guess will be in the vectors. Oh, it's probably not in this. Probably with it. Not right. But Geojson, yeah. The section results. You can go even from here. Water pump locations is the final output. You can download it from here, and we can open it on QGIS if you have installed. You don't need to do this operation, just to give you, well, as well, a taste of QGIS environment. We add a base map, and we are here in Teni district, India. We find the 2 suitable areas where a water pump can be installed. This was the end of this exercise, GIS exercise. I will go back to my slides for an introduction on remote sensing. But first of all, I would like to know if there are some questions, some doubts. Please go ahead. It would be nice to have an open discussion on this.
I actually enjoyed it a lot. Like, I've never used Geopandas before, but I can imagine you can also use this for a lot of other I should call it like vector calculations. Like now, of course, you use it specifically to map coordinates as well, which is not always relevant in that case, but the intersection, etc., those functionalities. I was imagining all these other use cases where you can use that for. Is that a common use case actually for this?
Yeah, yeah. Sometimes suitability maps are the ones that we've been working most of the time when we work with GIS related projects. So basically, it's always a matter of finding the best or the most suitable place for something. obviously with so many other layers that this makes this exercise super easy to do. And I totally agree with in your field of expertise, especially for Earth observation in general, you don't really need to have an actual CRS, because image recognition or segmentation or object detection are usually just can stay just in one image, and applying the model to that image. That doesn't have to have the geolocation factor. If I think about other operations, we have some operations for example, find the closest path of vectors. So for the project that I mentioned before in Indonesia, we launched the alerts. As you can imagine, these alerts are in the middle of the forest. There are no infrastructure, or at least mapped infrastructure, and how to reach to these locations in the fastest way to have a rapid response to the alerts and to the danger. We had this, we developed, for example, this fast route linked to the optimization of the network with the mapped through GPS Garmin stations. So it's different according to the type of application and project that requires. But yeah, Geopandas is actually a nice library to work with geospatial data. I would say.
Yeah, very cool.
Are there any other questions from the participants? How's it going, first of all? Like, you able to follow? I'm going too fast, too slow? Is it too easy? Because yeah, again, these are the basics, and trying to deliver some basic knowledge on this, but it's really actually an introduction, and the same will be for the remote sensing parts. But in your domain, I guess the remote sensing part is more interesting, because yeah, you can actually use satellite-based data to detect objects from space. So this is really, I guess, interesting as well for you. I have to say, in the AI domain, for example, something that we usually use on a daily basis is the classification of random forest classification for land use, for example. Land use, land cover, something that many clients request, and to see these changes over time. So this is something that we do quite often. But yeah, if there are no other questions, I will go ahead with remote sensing part. Or probably I'm missing the chat. Oh yeah, there are some questions. Yeah, I will share the notebook and the presentation as well. Yeah, please, Sako, if there are some pushing questions, stop me. Yeah, I guess the comments here in the chat are quite a lot. Someone having some issues. Yeah, I will anyway. Yeah, please, let's come back to me. I will leave you my email address, so if you have some issues with using certain packages, or if you want to know more, please contact me even later on. For the purpose of this webinar, we can go ahead now with the remote sensing part. And yeah, I want to start with the actual questions. Remote sensing, it means, and pose you to the question before starting with the actual description of the remote sensing. Do you think that your eyes are reliable? Basically, studies have proven that our visual systems is strict most of the time, because we don't need to let the brain work all the time 100%, and the brain then trying to fill the gaps. And I want to pose you this question, trying to look at this video and focus on this square and tell me what is the color of this square. or if basically the color of this square is changing or not. At first sight, yeah, it seems that actually the color of this small box is changing, but is actually the same. Our perception of the color is just due to the different background, so the different graduation and different context that box is in. And another nice example is about, I was talking about the filling the gaps. And first sight, this image looks in colors, but it's just a black and white image with some stripes. And basically the brain fills the gaps and you kind of see this color, especially where the lines lie in colors. And this is another example with text about the same image. Well, why talking about this? Because remote sensing and our site, it's a kind of remote sensing, and remote sensing is basically the process of detecting and monitoring the physical characteristics of something that we have afar. And measuring is reflected and emitted radiation. This is the same when we look at something that is just next to us. So basically, shortly, we can talk about remote sensing every time there is a sensor that is measuring something or an object at certain distance. We have different type of sensors, so UAV or drones, aerial television, airborne or spaceborne, and in our case we will be focusing on satellite spaceborne, then sensors, mounted sensors. Satellite types. We have different type of satellites with different goals, and they were developed for different purposes. As you can imagine, the ones that will be focusing our attention today are satellites that are Earth observation ones, and they record information on land, vegetation, water, and oceans. I showed before a slide that was a bit recapping the commercial, non-commercial satellite that we use for that specific project, but here is a bit broad overview. So we have the digital globe satellite and Airbus planets. They are the main ones that are commercial ones. High resolution imagery, ESA and Landsat and MODIS. The first one is the Sentinel project by European Space Agency, and the second two from NASA, non-commercial. When we talk about satellites, concept to review again is the type of sensors that we have mounted on this satellite, especially Earth observation ones. So we can distinguish between two types of sensors, passive and active. The passive one is what we call more general optical imagery. So they record optical imagery. What are some examples are written there, but how does it work? Basically, there is a source, that is the sun, hits the surface of the land, and this reflectance is recorded by our satellite. We have the other system, which is active. These are some examples. For the Copernicus program, we have Sentinel-1, for example. Active systems that work differently because we have the actual satellite, the actual sensors that send the signal on the surface. This is bounced back to the satellite and is recorded. So this backscatter is recorded. What are the pros and cons of these two type of sensors and then actually images? For the passive systems, well, they are the most easy to work with because they are close to what we can imagine as a picture. The camera does the same actually, so you can't take an image with your phone on the dark. But the big cons is that we record the clouds too. So we don't penetrate the clouds. And if the area of interest is cloudy, there's cloud coverage. Basically, we got back clouds, so a white screen. For the active system, big cons, I would say, probably a bit more complicated to understand and to work with, because they are characterized as well by some noise, and so it needs to filter this data. But the big pro is that these images are not affected by cloud coverage and can be collected as well at night. So nice factors. Resolution types. We have three types of resolution. We can go quickly look at them. As you can imagine, well, a low resolution is a resolution that has a big unit system. So the unit, the pixel is big. High resolution, the pixel is smaller. So the correspondence on the ground is for example, this image 30 by 30 centimeters means that the smaller things that I can detect has to be bigger than 30 centimeters. Temporal resolution is actually what we call revisit time. So satellite obviously has orbits and goes through this cycles. What is the time that the satellite take to go back to the same spot on Earth is called revisit time. As you can imagine, for the commercial images and sensors, we have just a couple of days or a day of revisit time. For the ones that are freely open, we have 5, 6 days, sometimes 12 for Sentinel-2 and 16 days for Landsat 8. Then when we actually have a project or a task to solve, obviously we have to have a balance between these two types of resolution, spatial and temporal, because obviously one type of dataset can be super high, have a super high spatial resolution but low temporal, and if we want to detect fires, it could be too late, for example, even if we can detect each cells and each centimeters of fire spread. So yeah, this is a nice overview of all this type of data sets in relation to spatial and temporal resolution. And then the spectral resolution is really important, because when we often work with the satellite-based data, we work with the multispectral data. So it's not just in the range of the RGB, so not just as our cameras, but expanded data range and spectrum. So yeah, satellites are the ones that we work with can register the visible, but even infrared, the near infrared, shortwave infrareds, and many other wavelengths. This is yeah, an example, or yeah, low and high spectral resolution. Obviously, a low spectral resolution has just 3 bands, for example, and the hyperspectral, so a high resolution, have many more bands. We can combine these bands to create different type of products, and actually the exercise will be basically about this. Just as an example, for each sensors we have, so Sentinel-2 has this list of bands. This doesn't mean that all the rest of the sensor has the same list. Could be different ones. So for Sentinel-2, blue, green, and red are band 2, 3, and 4. For Landsat, probably will be different. And as I mentioned before, well, the natural thing that we do when we see when we look at, for example, a Google Alert, Google Map picture, is RGB composite. So in the case of Sentinel-2, we just combine the band 4, 3, and 2 to create a true color composite. Well, with the same image, we can actually change the composition of this band. In this case, for example, we added, instead of the red, we have the near infrared, and we got this for a false color composite. And this, for example, is a good method to announce vegetation. Another thing that we can do with bands are actually some calculation with bands. So the result of this calculation can be and often can be used for vegetation index calculation. So the most used one is the NDVY, so normalized different vegetation index, and basically take the near infrared band and the red and the subscription, and then basically is normalized. So it has values between -1 and 1. -1 means bare soil, so no vegetation or status of the vegetation really with low chlorophyll, and values that are closer to 1 means really good vegetation status. Just to recap a bit, what are the benefits of the Earth observation technology? Obviously, we can cover large areas. We can scale up the product. As I mentioned, the spectral resolution, we have sensors that are capable of recording multispectral imagery. We can fusion this data set with in situ measurement, so to validate and to make a better models. We have real-time data. This obviously depends on the revisit time, on the temporal resolution, directly digitized, and we can basically have less costs and be more efficient, effective with costs, because we can scale up this analysis to bigger area. Well, non-disputable information, because we found, for example, in our project lately, we've been involved with the Amnesty International to detect deforestation in a region in Vietnam, and for the government or for the entities, local entities, there was nothing going on. The reports were saying that no deforestation at all, but using satellite imagery, you can actually say otherwise. It's time to go for another exercise. So this time we'll go to the second part. It's a remote sensing exercise. And what is this task? Is basically play a bit with the Sentinel-2 image calculation of some vegetation index, and as well to map this index and have a difference between this vegetation index. The rasters that you find in your folders here are the Sentinel-2 for February 2019. Sentinel-2 for February 2020, and then already a calculated NDVY vegetation index for February 2020.
Hi, sorry, Federico, please. Before we start with the exercise, there are questions in the chat about certain types of satellite.
Yes, please.
First, Kamal asked, they are currently researching dying rivers. So he asked, which satellite or space mission is particularly relevant to water sources like rivers? Yes,
for sure, a feature that Sentinel-1 can be super useful in is the water detection, because basically in active systems like the radar ones, the backscatter is not recorded back. It doesn't bounce back to the satellite, so it got absorbed by the water or liquid substances. So in a normal Sentinel-1 picture, probably I can show you later on, you will see grayish and white in the lens, and a total black pixels for water bodies. We actually use this Sentinel-1 to detect water bodies of the surface. We are not able to go deep into the surface, but at least to, for example, something that I think is to check what was the status of the river, lake, or even the coastline 5 years ago, and what is now. So to have two images, compare two of them, and this is already a nice analysis. So change detection analysis using Sentinel-1.
I think that clears everything up. So we have another question. Which open source RS data do you recommend for monitoring forest and vegetation?
Yeah, actually,
sorry,
in this
the question still has a second part. It specifies, would you rather go with Google Earth or Sentinel-2?
Yeah, well, Google Earth is what we see in Google Earth is basically just one image, probably if we are lucky, per year, clean up by clouds, so no clouds at all. So when in this type of analysis, this is not really feasible, because it could lead to misleading results. It means that what we see in Google Earth, it's a mosaic of the best images that are out there, clean out, and something could have changed between two mosaics, for example, two acquisition dates. Sentinel-2 has lower resolution. Well, just to clarify, Google Earth use digital globe images. So our commercial images 30 by 30 centimeters. Sentinel-2, on the other hand, we have each 6 days, 12 days in some part of the world, this time revisit time, 10-meter resolution. So the resolution is a bit lower, but we can actually do a proper assessment for this vegetation index. And Sentinel-2 is multispectral, medium multispectral resolution. So for monitoring forest and vegetation, Sentinel-2 is a good option. As an active system, Sentinel-1 as well. My thesis was about detection of deforestation using Sentinel-1 and CNN model. So just basically detect the changes in vegetation, because obviously the vegetation comes less, it's clear out, the backscatter is different. So you have a different response, and you can actually try to detect this pattern.
Okay.
I see another question here. Which open source? How did you figure out that certain pulse spectra indicate certain structures, like the vegetation, for example? Well, this is a good question, and open up a nice discussion about how useful is remote sensing, or what are the limitations of remote sensing. You always need to have some field data. We never conduct analysis, and we give our result without even having someone from the field or even a picture. You always have to know what is the landscape, what it looks like, and then trying to use this in situ data information to then scale up with the remote sensing data. Oh yeah, marine leader. This is it depends on the entity of this leader. You know, if it's if this is covered for the amount of litter is greater than 10 by 10, why not? You can actually detect it. I don't know how is expanded the problem. If it's just a can or a bottle, obviously not even with 30 centimeter resolution we will be able to detect litter from space. You have to always look at this spatial resolution. I hope I answered, Naman. Great. Yeah, so I pretty much like this question, so please go ahead. if you had more, or save for later on, we can go ahead with the with the exercise on remote sensing part. So I was telling you about the data set. We need to import again, or some packages that we need, set again our working directory, and start to read some images. Here we go. So we can now open the image with Rasterio. Rasterio is a package that, as for Geopandas, we use it for vector files. Rasterio is basically essential to use it for raster files. So what we're gonna do now, we will open the Sentinel-2 of 2019. So I imported rasteria as IO, so IO that's open, and we open the 2019 image file. Here we go. Well, this is open. We can now explore a bit metadata of this data set, this raster. We simply write the name, Sentinel-2, 2019, and yeah, type.meta. So let's see what the metadata says. Well, it's a GeoTIFF. We were talking before about different formats of the vectors. Specifically, we talk about S3 shape files and GeoJSON. A really common raster, GeoRaster, is a GeoTIFF, so GTIFF. Usually we have TIFFs which don't have the geospatial factor. This time we have a GeoTIFF with all this information as well as the CRS. We can check it out instead because we know the Sentinel-2 is a multispectral data set. What are the bands contained into this raster? And we do this printing list of bands for the specific one. So S2 2019 dot description. So with the description, we will have the name of the band in the raster. So as you can see, we have from B1 to basically B12 or like different wavelengths, and then we have some quality bands at the end. It's not super relevant for our exercise so far. But yeah, an important point is that specifically with these packages, if we want to visualize this data, we need to normalize them, and we will use this range to normalize. So we can just run this cell, we normalize it, and then, well, these are the bands. We can give them the name. So for the near infrared, for example, the band is the number 8. I can show you again this table. So band 8 near infrared. We have for the red band 4 over here, and so on. So we will need just the near infrared, red, green, and blue, and shortwave infrared for our purpose, our exercise. So once we read and we give this the names, we normalize. We just need to run these two cells. And finally, we can now use these bands, make a stack of layers. Just a recap, I'm sure you're familiar with this, but yeah, we have 3 main channels, usually for visualization. Actually, we could use just 2, but common uses to use RGB. So if we want to actually have a true color composite, we have to put in these 3 bands RGB, the actual bands RGB, so red, green, and blue. So we can basically take it from here, so the reds, so R, to create the stack, comma, the green, and the blue. Don't forget comma. And well, we just plot them. We plot this RGB composites. This is just some parameters of the plot. If you run this cell now with this composition of the band, what we will see is actually the Sentinel-2 image. As you can see, it's not really nicely visible. We need to adjust a couple of parameters. Most of the time is the range of arrays that we use, the range of values that we want to use for better visualizing this. We can change these visualization parameters, just change running the cell. The array min and max were already arranged here properly. So if we run this cell, we will have this does the same thing of before, we will have a clear picture of Sentinel-2. This, I believe, I download this from an Indian region as well. Well, this is a true color composite of a Sentinel-2. The colors, because it's a true color composite that you see, are the ones that our eyes are used to see. So blue for the water, we have sand here, we have some infrastructures, some fields. Well, we are capable to do much more with this type of data, because we're talking about multispectral data. So we, for example, can enhance the vegetation using a different type of combination of bands. To be a bit faster, I will just copy and paste this combination. So the true color composite, changing the first one. Changing the first one. Because to enhance vegetation, for example, we can combine the near infrared, the red band, and the green band in this order. So near and the normalized one. And we can show this false color then, how it's called, because this is called true color composite. And that is called false color composite. As you can see already, features like clouds are well visible in both type of visualization, but vegetation is a bit more clear here, because well, I should supposed to zoom in a bit more, but we can distinguish really quickly the water bodies and the urban areas instead of in red the vegetation. We can do the same thing, but stacking other three type of bands. I would just copy in this line as well. And in this case, with this band composition, with this example, we can enhance agricultural fields and some patterns that are not visible in the actual RGB composite. I will add this here, the shortwave infrared. We'll have the near and the blue. So let's plot this again and again. This is just basically an example on how combining different bands with no calculation at all, we can already extract some usable information. Here, for example, I see that, well, what is water, what is not, what are water bodies, to go back to the question of before. With this type of visualization, the same data sets, different bands, you clearly see what is the water. And a further step that we can take is the vegetation index calculation. I mentioned this before here. So this NDVY, it's a calculation of bands using the near infrared and the red band. So we have to just allow the environment to divide by 0, because it could be the case actually. The NDVY, and we calculate the NDVY for 2019 pictures. So we specified here the type of data format. We don't need to do this for the actual division. So if you remember about this formula, a normalized formula, we actually take the near infrared bands minus the reds and divided by near infrared plus the reds band. So this is this formula here translated in scripting, and the NDVY is calculated. The only thing to do now is just to plot it. Once we plot it with a specific as well visualization parameters, this is the result. As I mentioned before, this dataset goes from -1 to 1. -1, it means water bodies or bad status vegetation. and instead greener in this case in this picture. So values closer to 1 represents greener vegetation. Well, this is already a nice analysis. For example, we find ourselves often to have clients that say, okay, I want to check over time how is it doing my vegetation or the vegetation in specific plots. If I need to give water, this is a bit could be towards the smart farming topic. It's something that we usually haven't used. But what we want to do as a final output today or tonight, actually, it's almost 8:30, will be to see check 2 NDVYs, so 2 vegetation index, and see the differences between the 2 of them. We run here into an error because this image that we created doesn't have any specific metadata. No worry about it. This code, just this cell allowed us to actually take the metadata of the original Sentinel-2 and paste it for the NDVY. And then, well, if we run this part of the code, actually is all about the data format. I don't want to go so super deep into this discussion right now, but we can focus our attention on actually this calculation, which is basically a change detection. It's something that we found ourselves doing this quite a lot. So it's the detection between 2 different images, 2 different rasters. Simply, we just subtract the NDVY for 2020. We have to read it first, I guess. Subtracted to the NDVY that we created. So the NDVY 2019. 2019. Well, with this, we find the NDVY different. We can save our input as well, because obviously it's nice to open this on other platforms or QGIS, for example, to better zoom in and zoom out and better displaying the results. We can open this this image with always the package rasterio and read it. So just run the cells and plot it into our Colab environment, and this is the result. So this is a negative positive changes map. So it means that basically higher the value, so closer to black here in this type of visualization. Actually, we had the change, a really high change features on the features on the land changed between the 2 images. We can visualize this. There is with matplot. Oh yeah, we should run this with matplots here. We can choose even another type of palette, another type of visualization. Well, let's go for the CVD. Let's try this. We can just set here CVDs. I hope I spell it correctly. Obviously not.
There's the space in front of CVDs.
Oh yeah. Here we go. Yes, and with this we can actually see the changes that occur between these 2 NDVY images. For example, we could have seen these changes as well in such an image, but yeah, this is the same difference between the 2 of them. So yeah, we're done with this exercise. I have just a couple of slides more. I guess we can go before, first of all, with some questions around if there are many.
I have not seen any more questions in the chat, so if anyone wants to speak up, then that's
there is this a question from Kamal about how to eliminate the clouds in such image, for example. So if we have an image such this, Kamal, it depends on the task to solve. So if our task is to have a clear image of the area for a specific classification or yearly image, then we can just do a mosaic. So we apply a filter to the clouds, and then you mosaic on basically the spots that in one image would be empty because the image is the cloud is filtered. It's fulfilled with the image below, for example. So you stuck a layer of Sentinel-2 that has less cloud percentage cover, and then you stuck them and you make a mosaic. As I mentioned before, this is not really useful when you want to run analysis, qualitative analysis type of research. And we decide in that case just to keep the clouds, or just to use another image that has less cloud percentage cover.
All right, then there's one last question. Why should we normalize the image in order to plot it?
Oh, yeah. I guess here is just a problem here that we have in Python. And then it's the range of mean and maximum that we give it to them. Because usually in such a, if you open it, I can try to open it. Will be super quickly on QGIS, on a GIS software, whatever, could be ArcGIS or QGIS. For example, in two different systems, the visualization by default will be different. You will actually see two different images almost, because the values or the range of the bands or the default bands maybe are not the same for everyone. Let's see what happens if I open a Sentinel-2. You see, this is what happens if I don't, by default, QGIS open the Sentinel-2 with such values. So often we find ourselves to change the parameters and normalize the bands. For example, yeah, I can do here, maybe stretching to mean and max is not the case. Let's try out this. No, this is exactly what I was not able to do. Or, oh yeah, I found the error. Actually, this is another band that we need to, for 3 and 2, for example. So then you see, we go to towards an actual true band, true color composite. And these are the eyes, our eyes are more understandable. Obviously, probably a deep learning model, in the case you will use one of them, will not be needed to do such a thing. But for better working and exploring and understanding the features on the land, we often find ourselves to apply some normalization. I hope I answered your question.
I believe so, yes.
Well, I guess I have the last slides. Yeah, basically the exercise that we had before. This is a nice practical example. This is something that I analyzed and ran some data displaying for fires in Sicily. This is really close to my hometown, original hometown. There was a huge fire, and then I wanted to check, basically there were 3 huge fires. I wanted to check what was the extension of these fires. And these are all the same files, basically. So the first one is a true color, this one is a true color composite, and the other ones are all false color composites. And as you can see in the true color composite, you actually don't see the line of fire here, for example. With the combination of the other ones, instead you're able to actually enhance certain features. So this is a bit a practical application of what is, according to the task that you need to solve, what is the best combination of bands. Yeah, I left here a couple links. Someone probably was asking before what was the best way to download actually and to find available datasets. The links from before were about vector files. These are mostly satellite-based data, so raster files. We have for sure the Sentinel playground, which is a nice way of visualize or a tool for visualizing the data. These are Sentinel-2. This was developed together, I guess, with ESA. And basically, this is called Playground. So the nice thing of this, you can just go somewhere else in the world, set your percentage of the clouds that you want to have the image with. And well, this is a true color composite, so natural color. So the bands used are 3, 2, and 4, but we could have the infrared. So to enhance vegetation already 8, 4, and 3. So the same kind of exercise that we did already, but these are already done. And from here it's possible to see globally the data. Instead for downloading, the ESA SheApp is the actual platform, the official platform of the European Space Agency for downloading this data. Earth Explorer is a nice tool as well. These are all links. So once I will deliver to you this, give it to you this presentation, we'll have the chance to explore these links too. And these are all platforms where you can check the availability of the data and download the actual raw files. Otherwise, we have nice tools as well, like Sentinel Hub and Google Earth Engine. They give you the chance actually, even through API and Python scripting, to access this data. And I put an example in the workshop at the end of the Collab environment here. You will need, for example, to have a subscription to Google Earth Engine, which is, by the way, for free, but still you have to register and it takes sometimes a couple of days. So that's why I wasn't sure to use this for the exercise, but then you need to use some packages, specific packages related to Google Earth Engine. Initiate Google Earth Engine, so link your environment with the Google Earth Engine, which is not super difficult, but still needs to be done. And then some collection, you will find some collection over there, and import the images directly in your personal environment. Let me check what else. Otherwise, there is actually Google Earth. So you could explore a bit, download and do analysis with Google Earth Engine already. It's a nice cloud platform. And just today was released actually that some Planet Data, there is a commercial satellite provider, were released on Google Earth Engine. And this is a free service. Basically, it's composed by, we have the scripts here and all your documents and assets, the scripting window and the console, and you can easily check it out in the map or whatever you script here. And for example, in the case of Copernicus, you can just go look for the Copernicus Sentinel-2 and check it out what is available in the datasets and the servers of Google Earth. So for example, this is the collection snippet, so you can retrieve Sentinel-2 from their datasets. I guess that, that's it. That was my presentation. I hope you enjoyed, and please, if you have some questions, now the time. Otherwise, we could always can always contact me. These are my contacts. Federico at Space4Good.com.
I believe there are two last chat.
Yeah, how do you know the combination of bands for a use case? It's a trial and error. Well, there is, I guess it was at the beginning, but now it's it's well studied. So there you can find a lot of papers, tutorials, and specifically for whatever feature we need to announce specifically for each data set. So yeah, you can find a lot of literature, scientific literature on this Ramkurumar. Wildfire detection. Well, near infrared, SWIR, shortwave infrareds are for sure the ones that announce the line of fire, for example. But yeah, the wildfire detection is for sure a hot topic, but it comes with the limitation of the time resolution. The revisit time that we've been talking about is not often good or enough to detect live or near real time this data. So you would need for that purpose some geostationary satellite. They always look at the same part of the Earth, and then in that case, whenever something is off, the alert is launched and the images and the information is spread. In the case of Sentinel-2, more than actually near real alerts, what we can do is what I show here basically. Well, in this case, the fire went on for 3 days or 4 days. So I was lucky enough that the satellite passed and recorded the line of fire. But often we find ourselves arriving here to find just the burn area. And there is a specific developed index, as we did for NDVI. There is an index called BNR, so the burn ratio area. So you can just basically announce the burn areas. You can do it as well already with some bands composition, but the proper one is creating this burn ratio. Yeah, burn. Sentinel-2. Yeah, normalized burn ratio Sentinel-2, and then you can Google like formula, for example, to see what are the bands that this use. So yeah, this is the formula. So it's used the band 8, which I remind you is the near infrared. You can look at the metadata, for example, band 8 near infrared minus the band 12. So it's in our case the shortwave infrared and normalized. So this is specific for burn area detection. Oh yeah, there was Janis that actually was explaining this. Yeah. Oh yeah. Cool. Are there any other questions?
I guess not. That leaves us to thank you very much, Federico. I at least learned a lot myself, and I already worked with a lot of data before, so it's always nice to get into a new domain and know of all the tools that you can use there and the way that they actually approach these types of issues before you try that just by your old standards, basically. So at least I'm helped a lot on this topic, but I also think that all the other participants here get a great head start with your knowledge. So thanks again. I'll also thank Alexander, but I'll thank him later for providing also the support. Yeah, I see a lot of thank yous coming in on the chat, so I'm not the only one who's grateful for your.
No, I'm happy. I'm happy to have this. Actually, as you can imagine, as a short introduction on the GIS remote sensing world, which is huge itself, but it's always changing. Like every day, there are new tools, there are new data sets available. It's always really an ongoing research, something that was basically impossible to think or to do a couple of years back before the Copernicus project itself, for example, which takes the name of Copernicus as a a third revolution of the data, because finally the data, satellite data, became accessible, and a company like us could base our core business upon this type of data. And then the computing power and all these new machines helped in the process of developing such applications. So yeah, I'm thankful for this opportunity to spread a bit this information. Thank you for participating.
Very cool. As a last comment from my side, I love the ratio of code that you already had there and the things that we needed to fill in ourselves. Like, that really made it highlight the points where we well, needed to learn, like, okay, this is how that works for this type of data, and also not be cumbersome with like typing how the visualization should look, etc., because that of course is the same for every image visualization. So really nice ratio there.
I will share a couple of slides of my presentation where are the most necessary and I guess important links to the data, so the participant can go over it them and trying to find their solution. And I wish you good luck.
Awesome. Yes. Thanks a lot, then, again, and to the rest of you, good night, or maybe even good morning to you. That depends on the time zone. Okay, thanks, guys.
Bye-bye. Thank you.
Yeah.
Thank you.
Bye.